Hello. We are just about ready for another recorded lesson with seventh graders. And today we're talking about magnets and magnetism. Now you've probably seen magnets. If you have a refrigerator at your house, chances are there's a magnet on it. Okay. These magnets might be holding notes or pictures, or they might just be there for looks. So if you have ever experimented with magnets, you know that they stick to each other and to some kinds of metals. You also know that magnets can stick to things without directly touching them, such as a magnet used to hold a piece of paper to a refrigerator door. It's not actually in contact with the refrigerator. There's a paper in between it, right? More than 2,000 years ago, the Greeks discovered a mineral that attracted things made of iron. Because this mineral was found in a part of Turkey called magnesia, the Greeks called it magnetite. And today, any material that attracts iron or things made of iron is called a magnet. Now, all magnets have certain properties, okay? For example, all magnets have two poles. Do you know what those poles are? I'm sure you do. You're right. There's a north and a south pole. And magnets exert forces on each other and on surrounding anything within their magnetic field. Okay. Now the magnetic effects are not the same throughout the magnet. What would happen if you dipped a bar magnet into a box of paper clips? Well, if you can imagine, if you had a bar magnet, I don't have one. If you had a bar magnet, okay, you dipped it into a box of paper clips, where would those paper clips stick? Would they stick here in the middle or on the ends? And in fact, they would stick on the ends because that is where it is the strongest. Most of the clips stick to the ends, and this shows that this is the strongest part of the magnet, okay? There's a north and a south pole. So suppose you hung your bar magnet on a string so that the magnet could spin, okay? And you'd see that one end of the magnet always ended up pointing north, and obviously the other end would be pointing south. Now it would actually be the south part of your bar magnet that points north, and the north part of your bar magnet that points south, okay? Magnetic poles are always in pairs, and you will never find a magnet that has only a north pole or only a south pole. When you bring two magnets close together, the magnets each exert magnetic force on each other. These magnetic forces result from spinning electron charges or electric charges in the magnets, okay? The force can either push the magnets apart or pull them together. The magnetic force is a universal force, and it's always present when magnetic poles come near one another. So think of the last time that you worked with a magnet, that you were doing something with a magnet. If you held two magnets in a certain way, they pulled together. See how trying to bring them together slowly, but they accelerate when they get close and they want to pull together, okay? If you hold them a different way, we're going to turn this one around, they push apart. Now you can, if it's a weak magnet, you can force them together. These happen to be kind of medium magnets. Still pretty strong, but I can force them together. But they don't want to stay together, okay? The magnetic force between magnets depends on how the poles of the magnets line up. Like poles repel, opposites attract. So if we had a north and a south, they're going to attract. Opposites attract. If we had a north and a north, they're going to repel. They're going to push away. If we turn both of them around, we have a south and a south, again, it's going to push away. So if you have magnets on your refrigerator, you can do this at home, okay? You can find out how they work. Now, a magnetic field exists in the region around a magnet in which the magnetic forces can act. The shape of the magnetic field can be shown with lines drawn from the north of a magnet to the south of a magnet. This particular magnet, north and south, are the flat sides of the magnet, okay? So it would go from the north around to the south. It's a loop. The loops get bigger and bigger, okay? And these lines map the strength of the magnetic force and are called magnetic field lines. The closer together the lines are, the stronger the magnetic field is, okay? And the lines around the magnet are closest together at the poles. Now, if they're closest together at the poles, what does that tell you about the magnet's strength at the poles? Right, it's strongest at the poles, okay? So if I went side to side, there's still quite a bit of repulsion there. But if I go pole to pole, there is a lot more repulsion going on. So I want you to imagine these lines, this is a little bigger so it's easier to see. These lines go from the North Pole around to the South Pole, and they never cross. These lines don't cross, okay? So if you've got a line here going around to here, and a line here going around to here, one here going around to here, they get wider out here, and they're very tight together on the poles. So it's a lot stronger on the poles. Some materials are magnetic and some are not, okay? For example, plastic, not magnetic. Human flesh, not magnetic. Metal, well, it depends on what kind of metal it is. For example, my ring, not magnetic, okay? But other things are. Other things are magnetic. For example, my USB cord is magnetic. And it actually is attracted to the magnet. Okay. For example, a magnet can pick up paper clips and iron nails, but it cannot pick up paper, plastic, pennies. It won't pick up pennies. Or aluminum foil, for that matter. So what causes the difference? Whether a material is magnetic depends on the material's atoms. So what the material is made of, the little things inside, okay? All matter is made of atoms. Electrons are negatively charged particles of atoms, okay? As an electron moves around, it makes or induces a magnetic field. The atom will then have a north and a south pole. Most materials, such as copper and aluminum, the magnetic fields of the individual atoms cancel each other out, so they're not magnetic. Therefore, these materials won't attract other materials, and they won't attract magnets either, okay? In materials such as iron, nickel, and cobalt, groups of atoms are in tiny areas called domains. The north and south poles of the atoms in a domain line up and make a strong magnetic field. Domains are like tiny magnets of different sizes within an object. And the arrangement of domains in an object determines whether the object is magnetic. Now, can a magnet ever stop being a magnet? Maybe that's why our papers fall off the refrigerator sometimes. Or maybe it's because somebody else is playing with our magnets and they drop the paper on the floor. At any rate, yes, they can lose their magnetism. They can, the domains of a magnet may not always stay lined up. And when the domains move, the magnet is what we call demagnetized, or it loses its magnetic properties. Dropping a magnet or hitting it too hard can move the domains. Putting the magnet in a strong magnetic field that is opposite of its own can also move the domains. Increasing the temperature of a magnet can demagnetize it. At higher temperatures, atoms in the magnet vibrate faster, and as a result, the atoms in the domains may no longer line up, okay? So that's why heating it up would make a difference. You can make magnets, in fact. I don't know if you knew this. You can make a magnet from something made of iron or cobalt or nickel, okay? Probably the most common thing would be iron, like an iron nail. All you need is to line up the domains in it. So, for example, you can magnetize an iron nail if you rub it in one direction with one pole of a magnet, okay? So you're just going to rub your nail in one direction with one pole of a magnet. And what you're doing is you're starting to line up those little tiny magnets in that nail so that they're all going the same direction. The process of making a magnet also explains how a magnet can pick up an unmagnetized object like a paperclip. When a magnet is close to a paperclip, some domains in the paperclip line up with the field of the magnet. So the paperclip becomes a temporary magnet. The north pole of the paperclip points towards the south pole of the magnet. The paperclip is attracted to the magnet. Now, when the magnet is removed, the domains of the paperclip become scrambled again. But as long as the magnet's in place, it can actually pick up other paperclips. So what happens if we cut a magnet in half? Okay, so I have a magnet here, and there's a north pole on this side and a south pole on this side. What happens if we separate the north and south pole right in the middle? Is this a north and this is a south? What do you think would happen if we cut it in half? Well, no, we don't get a north and a south magnet. We still have a magnet over here that has a north and a new south end. We have a magnet over here that has the south, the original south, and now a new north end, okay? And every time we cut it in half, the same thing happens. North and south on this one, north and south on this one. A magnet has poles because its domains are lined up. Each domain within a magnet is a tiny magnet within a north pole and a south pole. Each of the smallest pieces of a magnet has two poles. So there's two poles all the way through this magnet. It's north, south, north, south, north, south, north, south, north, south. We separate them, it's still north, south, north, south, north, south, north, south. South on this end, north on this end, okay? There are different ways to describe magnets. Some magnets are made of iron, nickel, and cobalt, as we mentioned before, or a mixture of these metals. And magnets made with these metals have strong magnetic properties and are called ferromagnets. Now, if you remember anything from chemistry, ferro, Fe, is actually the atomic symbol for iron, Fe, ferro. Ferromagnets are magnets made up of these metals. The mineral magnetite is an example of a naturally occurring ferromagnet. Another kind of magnet is the electromagnet. This is a magnet made by an electric current. An electromagnet usually has an iron core. Okay? We use electromagnets when we have to use large industrial magnets. The nice thing about an electromagnet is when you turn off that electrical charge, you turn it off, you turn the switch off, the magnet turns off. These are not electromagnets. These are permanent magnets. They are magnets all the time, okay? There's no little light switch on the side that says we can turn it off, okay? It's always on. Electromagnets can be turned on and off. So we've got permanent magnets and we've got temporary magnets. We've got two different types of magnets. Magnets can be described as temporary magnets or permanent magnets. Temporary magnets are made from materials that are easy to magnetize, but they tend to lose their magnetization easily as well, okay? Soft iron is iron that is not mixed with any other material. It can be made into a temporary magnet. Permanent magnets are difficult to magnetize. So if it's difficult to magnetize, what is it also? It's also difficult to demagnetize, okay? They tend to keep their magnetic properties longer than temporary magnets. Some permanent magnets are made with alnico, an alloy of aluminum, nickel, cobalt, and iron. Now, I don't know if you've thought about this before or not, but I happen to know where the biggest magnet in the entire world is. Anybody guess where it is? Okay, so the biggest magnet in the world is actually the Earth. Trick question, okay? One end of every magnet points north if the magnet can spin. You know, if you got like a compass, the north side of a compass will point north. And for more than 2,000 years, travelers have used this property to find their way. In fact, you use this when you use a compass, because a compass has a free spinning magnet in it. One giant magnet in 1600, English physician named William Gilbert suggested that magnets point to the north because Earth is one giant magnet. In fact, the Earth behaves as if it has a bar magnet running through its center. The poles of this imaginary magnet are located near the Earth's geographic poles. Not exactly, but nearby, fairly nearby. If you put a compass on a bar magnet, the marked end of the needle points to the south pole of the magnet. Does that surprise you? Well, opposites attract, right? So north is going to be attracted by south. A compass needle is a small magnet, and the tip of that points to the north of the needle's north pole. Therefore, the point of the compass needle is attracted to the south pole of the magnet. Okay, so if we had a compass here, and we took a magnet, and we knew this is the north pole, and we put it near the compass, that needle, the north needle is going to point away from the north pole. The south side of that needle is going to be drawn to the north pole, okay? So we have compasses and they point north, right? That's what we've always been told. They point north. Is that the Earth's north pole? No, if they point to what we call north, that is actually the Earth's south pole. Which means if Santa's in the North Pole, then he's actually in Antarctica, not up by Alaska. Sorry. Because the compass needle points north, that tells us that the southern magnetic pole is actually near the northern geographic pole. So it's the opposite of what you might think. Although you think the Earth, you can think of the Earth as having a giant bar magnet through its center, there really isn't a magnet there, okay? The temperature of the Earth's core at the very center is very high, and the atoms in it move too violently to stay lined up in domains. Scientists think that the Earth's magnetic field is made by the movement of electrical charges in the Earth's core. The Earth's core is made mostly of iron and nickel, and the inner core is solid because it's under a great amount of pressure. The outer core is liquid, and because the pressure is a little bit less there. Still a lot of pressure, but less. As the Earth rotates, the liquid in the core flows, and electric charges move, which makes a magnetic field, just like we talked about before. Now, has anybody ever seen the Aurora Borealis? Raise your hand if you have. Okay. Some of you have seen pictures of it. I actually saw it once when there was a really big solar storm. Okay. Ionized particles that passed through through space and came in contact with Earth and interacted with the magnetic fields. And I was living in Boise at the time, in Idaho. Normally, we don't see the Aurora Borealis there. We're too far south. But because the storm was so big, I actually saw the Aurora Borealis. It's really, really cool. It's not only lights, there's actually some sound that goes with it too. You can hear the ionized particles in the air. The Earth's magnetic field plays a part in making auroras. So there's northern lights, and there's also southern lights too. Never seen those. The aurora is formed when charged particles from the sun hits oxygen and nitrogen atoms in the air. And the atoms become excited and then give off light in many colors. And the Earth's magnetic field blocks most of the charged particles from the sun, but the field bends inward at the magnetic poles. And as a result, the charged particles can crash into the atmosphere at and near the poles. So remember, I showed you how the magnetic field comes around like this. Well, as the charged particles come across space and they're attracted in, it's like a funnel. They just kind of go right into that center piece, right near the poles, and it ionizes the air right there, all of the nitrogen and oxygen, and it lights it up like a neon light. It's really amazing to see. If you ever get a chance to see them in person, you should. The auroras seen near Earth's North Pole are called the Northern Lights, or the Aurora Borealis, and the auroras seen near the South Pole are called the Southern Lights. Yes, very good. Or the Aurora Australis. Okay. So that is all we're going to talk about on magnets today. I hope you enjoyed it, and I hope you learned something new. I also hope that you took some notes while we were talking. If you didn't, this is a recorded lesson, so you can watch it again and take some notes, because that will help you later as you study and as you go through this lesson on magnets and magnetism. It's, as always, been a pleasure for me to be here with you, and I hope you have a wonderful day. We'll talk again later, and we'll see you. Bye. Stay healthy. Stay happy.